Hello, I'm James Clark from King's College London, and in this brief video I'm going to look at nonlinear regression in GraphPad Prism. Unlike linear regression, which simply involves plotting a straight line through data, nonlinear regression can involve a number of different nonlinear models. The use of these models will of course depend upon your experimental design and might include enzyme kinetics, inhibition or enzyme activation studies, or simple biochemical interactions. For the sake of this demonstration, we are going to use synthetic data showing both response and inhibition. In this first example, we have entered data corresponding to the response from two different drugs. We have entered log concentration on the x-axis and two sets of n equals 3 replicates for group A and group B. We can view these as a scatter plot in the graphs section of the navigation panel on the left-hand side. You can see that response 1 appears to have reached a slightly higher plateau than response 2, and we might be keen to see whether the EC50 has been affected. It is worth noting in our data table that we have entered these data as log concentration on the x-axis. Normally, for these kind of studies, one would use log concentration, as it converts the graph that is formed from a hyperbolic relationship to a sigmoid relationship. And with a sigmoid relationship, it is better optimized for determining EC50s, etc. In order to carry out a nonlinear regression of these data, we go up to the Analysis toolbar and click on Nonlinear Regression. You will see the parameters nonlinear regression options box on the screen. There are many options to choose from for nonlinear regression, and over the course of this short video, I will highlight the most important ones to consider. The first is your model. In this case, we have a dose-response stimulation curve. So we choose an equation from the dose-response stimulation options. We know this is a log agonist versus response, and I'm going to choose the log agonist versus response 3 parameters, as I believe this fits my model best. There are many other curve types to choose from, and it is worth doing your research to work out what model you think your curve will be fitting. Under the Methods section, we can choose how we handle outliers, the fitting method, how strict our convergence criteria are, whether we have any weighting, and how we're going to consider our replicates. We'll deal with outliers in a minute, but for the moment we're going to consider each replicate y value as an individual data point rather than considering the mean y values for each data point. We can compare two different types of curve fit to try and determine which model our data best fits. We can constrain our curve to fit our data. For instance, in this model, we can constrain the bottom, the top, and the log EC50 in order to guide Prism in the curve fitting. You can enter initial values or ask Prism to calculate these automatically. For instance, if you know what your negative control and positive control are, you can enter these here under bottom and top in order to constrain your curve within a certain range of y data. You can choose the range of the x-axis where you want your curve to be fitted. Again, if there are any concentration outliers beyond the range of the curve you wish to plot, you can enter them here and save Prism from trying to calculate a curve fit for an area of your data that you do not wish to fit your curve to. The next option is your output. For every curve fitted, Prism will automatically create a results table and plot your curve on a graph. If there are no graphs currently plotted for your dataset, Prism will generate a graph automatically if you choose to do so using this option. Here also, you can choose how your p-values and your significance are displayed. There are a number models to choose from at the bottom of the screen. Relating to confidence, you can calculate your confidence intervals. You can set your confidence between 90 and 99% as default, or select a custom range. You can choose how your output of confidence intervals is formatted on the page. For instance, here we're going to do the range in brackets from one number to the higher number, or we can separate our lower and upper limits for convenience. Here you can also plot your confidence and prediction bands for your data set. For instance, we might want to click on this and choose our 99% confidence intervals, which will give us an indication of how robust our fitting is for a given data set. We'll deselect this and move on. In the diagnostics section, Prism will calculate your goodness of fit, for instance with an R-squared, adjusted R-squared, or sum of squares. You can also carry out a normality test on your residuals to confirm normal distribution. If you've chosen to do this, you can also plot a graph of residuals. Finally, in the flag section, you can flag up parameters of interest. For instance, when calculating a goodness of fit and your R-squared value is less than a predetermined number, you can enter that here, and Prism will tell you if your data are not a good fit according to these parameters. Since we are doing this as a simple demonstration, we'll make sure our model is selected correctly and press OK. The results section and generated table now show us a summary of our two datasets. The best fit values, EC50 and SPAN, are shown, including the 95% confidence intervals and our goodness of fit, including our R-squared value. For convenience, Prism also plots the number of X and Y values analysed just to confirm if there were any outliers should that have been selected. We can view this as a graph, and we can see our green and red line corresponding to response 1 and response 2 seem to fit very well. In this second example, we have entered synthetic data corresponding to a dose-response curve. If we look at the graph, you can clearly see at 10 to the minus 8 concentration there appears to be an outlier. We have entered this rather obvious outlier to demonstrate Prism's ability to discover outliers. Again, if we click on Nonlinear Regression from the Analysis toolbar, choose the same curve that we fitted previously to these data, and this time in the method, we choose Detect and Eliminate Outliers. At this point, we can also get Prism to generate a table of clean data with those outliers removed. Leaving all the other settings as they were, we can click on OK. You'll see immediately that when the graph is plotted, the outlier is highlighted, in this case, in red. This outlier is not included in the analysis or the curve plotting, or in the calculation of any of our experimental parameters. Prism can also calculate unknowns from a standard fitted curve. For instance, in this dataset, we have entered our curve data at the top of the table, and underneath on rows 11 and 12, we have entered the response data for two unknowns, and from this we wish to calculate or estimate what the log concentration of our drug would have been in this response. This time, when we click on Nonlinear Regression from the Analysis toolbar, and from within the option box we saw before, we can click an option to interpolate data. There is a second option, shown here to the right, which says Interpolate a Standard Curve. If you click on this Standard Curve button, you are given the option to choose which model you wish to use. In this case, we'll choose a sigmoidal with X as a log concentration, and underneath we have the option to remove outliers as before, and in the Options section we can choose how we report each of our interpolated values. In this case, I'm going to choose 95% confidence intervals. Once we've finished, we can press OK, and the results table will show us a calculated log concentration for each of our mean values. If you wish to examine your replicates, the second tab of this results page will give you each of your replicate estimations, and the table of results will give you a summary of your curve fitting information. It might be that you are unsure of which curve to fit. So returning to our original outlier dataset, we are going to re-examine these data and compare two different models. To do this, you go to the Results section, and you can click on the Nonlinear Table of Results section, or on the Change Parameters of Analysis, or press Ctrl or Command T. This will bring up the nonlinear regression parameters control box again. This time, we are going to use the compare function, and we are going to compare two different equations. In the middle of the page, we get to choose which equation we want to compare with our first equation. I'm going to scroll down and choose dose-response stimulation, and I'm going to choose a 4-parameter variable slope response. Once you've chosen the options you want, you click on OK. Prism will then do a simple analysis to see which curve fits your data best. You can see in the results panel that a null hypothesis of log agonist versus response 3 parameters has been formed by Prism, as this is the equation we originally chose. An alternative hypothesis is that the second equation is the correct equation. Prism has compared the R-squared values and the goodness of fit, and in this case has concluded that you must not reject the null hypothesis and that the log agonist versus response 3 parameters is the correct curve to use under the circumstance. If our second curve fitted better than our first curve, our p-value would be considerably lower, and Prism might recommend that we reject the null hypothesis. In our last example, we're going to look at inhibition data in order to calculate an IC50. We can see a graph of these data here. We have also entered information for controls, both positive and negative, which gives us an indication of the range of our inhibition. This is a compound graph consisting of data from two separate tables, as highlighted by the two bold tables in the Tables section of the navigation pane. In order to analyze these data, we click on Inhibitor Data and choose Analyze Nonlinear Regression from the menu. Since this is an inhibition study, we go down to Dose Response Inhibition, and we'll choose a log inhibitor versus response 3 parameters to fit. We then press OK. Prism reports a best fit value for top, bottom and IC50. We can view these data on a graph, and you can see the inhibitor data fits very nicely. While this analysis gives you an estimation of the absolute IC50, in other words, the concentration of agonist that inhibits your response by 50%, we might also want to look at the relative IC50. In other words, in the range of data that we have acquired, how much concentration is required to lower our response by 50%. In order to do this, you need to normalize your data. Prism has a very handy normalization analysis tool, and we have already normalized our data, and here are the data plotted as a normalized data set. Now our data range from an average of 100% response to the lowest response seen in our experiment. Now we can reanalyze these data using our nonlinear regression to calculate our relative IC50. By clicking on the Nonlinear Regression button on the Analysis toolbar, we can choose from the Dose Response Inhibition and click OK. Now if we look in our results, the IC50, which is 5.047 times 10 to the minus 6, is our relative IC50 for this dataset. So in this short video, we've looked at many different ways of analyzing dose response and dose inhibition data. The key to analyzing your data is firstly to understand the model that you think your data might fit to, and the second is to understand the many options that Prism gives you in order to analyze your dataset.